Yeah. Yeah, just one more minute, we can do it. Yeah.
Okay.
Yeah. Okay, now you can start. You can use the microphone. Yeah.
Sure. Hello everyone, just making a quick announcement before your lecture begins. My name's Niall and I'm in third year doing Maths with French, and I just wanted to alert you all to this conference that's coming up next week. It's called MIMAC, so Manchester Interdisciplinary Mathematics Undergraduate Conference. It's going to be next Thursday and next Friday, 2 full days with student presentations by some of your peers, industry talks from some quite big companies like DeepMind, Meta, Bearings, and so on. So yeah, I suggest that you all check it out. Like, there's loads of emails going around with more details. Go along to some of the talks if you're interested. There's some cool topics like neural networks, and also stuff that you're more familiar with, like some of the geometric stuff. And yeah, when I was in first year, there was never a conference like this, so I think it's a great time to check these things out before you decide what you're going to specialize in your future years of study. Thank you. Can I leave that there?
Yeah.
Yeah.
Thank you, Neil.
Yes.
See you. All right, guys. Good morning. So as Neil said, Neil took this course 3 years ago, and as you said, if you have time, attend this conference. It's next week, 31st and 1st of April. So it's Thursday and Friday of next week, okay? All right, guys. So a couple of announcements as usual. The quiz number 6, which is this one, is due by 11 a.m. today. So if you haven't done it, so please try to do it by 11, right? And also I'm really disappointed with the attendance in the lab sessions and also the attendance in the review sessions. So if you haven't been to any of the lab sessions this week, please, there's a lab session this afternoon at 2 o'clock in the computer cluster. So please do attend that one because the attendance has been very poor. I'm sure there are many of you guys who did not come to the lab session. So please do come to the one at 2 p.m. today, right? Okay? All right? Okay. All right. Now, I ask you guys to just watch this only one video. So this is the video that I asked you guys to watch. I hope there were 10 examples. I mean, this video presents 10 examples on MLE, maximum likelihood estimation. I hope you did watch this. I know it's a long video. It's 1 hour and a bit, right? I hope you guys watch this. So I'll just ask you to, like, this is the handwritten stuff. So this is example 1, example 2, 3, 4, 5, 6, 7, 8, 9, and 10. Like, is there any particular example you like me to go over, guys? So out of the 10 examples, talk to me, guys. I'm not going to bite you. Huh? Is there like, okay, let's start with example 1. Are you okay with example 1? Yeah? Yes? No? Example 2. Are you okay? This is oh, come on. What's wrong with this mouse? Are you okay with example 2, guys? Yes, everybody okay? Example 3. Any problems? You don't be shy to say no. I'm here to help you guys. And example 4, are you okay with that? Yeah? Example 5. Anyone has problems with example 5? 6. Example 6. No? 7. Are you okay? 7 is a little bit different. Are you okay with 7? Or anyone have problems? Come on, guys. Talk to me, guys. Are you okay with example 7? Or you want me to go over? All right. Then this is example 7 is a bit long. Example 8, I think this should be okay. Example 9 and 10 are on the invariance principle. Remember, one of the properties I talked to you last Friday during the review session was the invariance principle. That is, if you have a one-to-one function of the parameter, you can use the invariance principle to determine the MLE. So that's so example 9 uses the invariance principle, and so does example 10, right? Okay, guys, so these are the 10 examples. I hope you did watch this, and if you haven't, I know you may have coursework before other courses or something, but if you haven't watched the 10 examples, please do watch those when you have time, okay? Okay? So what I'm going to do today, guys, is to do some more examples as usual. So I'll start with this is example number example 11, right? Right, so here you have a random sample from a distribution this is the PDF or the probability density function, and we want to find the MLE of theta, right? Okay, so what do we need to do? The first step, let me go back to the review session last week. So if you remember the review session last week, the procedure that you need to follow is this one here, right? You need to follow 4 different steps. The first step is to write down the likelihood function. Step number 2 is to take the log of the likelihood function. Step number 3 is to take the derivative with respect to the parameter and set it to 0 and solve for theta. And step number 4 is to make sure that the solution in step 3 corresponds to a maximum. So you do that by taking the second order derivative and making sure that it's negative at theta equal to theta hat, right? So let's try to do the first step. So the first step is right? Now, if you simplify this, once again, it's really, really important that you do know how to simplify products of functions. And once again, I think I showed you one of my videos. You should look at, you should forward to, I'll show you once again. This is the video on how to simplify products of functions. So these are some properties, you can look at it, right? Now if you use these properties, I'm not going to show you, I'm not going to go step by step, but I'm sure you know. Now if you use these properties, this is what you will get. So this is the product of this function from 1 to n is equal to this, right? So that's step number 1. So let's go back to this. Step number 2 is to take the log of the likelihood function. Yeah? Okay, step number 3 is to take the derivative with respect to theta. Okay? And you set this to 0 and solve for theta, right? So this implies that theta hat, whatever the solution that you get out of this, you call it theta hat. The theta hat means it's an estimator of theta. So that's why you put the hat, right? Okay, so this is going to be 2n divided by the sum of xi, I from 1 to n. So this is 2 divided by the sample mean. Remember, the sample mean is simply the sum of xi divided by n, right? All right, that's step number 3. Now, step number 4, we need to make sure that this solution corresponds to a maximum, right? So you do that by taking the second order derivative, which is the first order, which is the first order derivative of this, right? So it's going to be minus 2n by theta squared, which is clearly a negative number, right? So the conclusion is that all right? You guys okay with this example? You okay? Any questions? You sure? Yeah? You good? Okay, guys? Feel free to ask questions, because there will, I mean, in the final exam, there will be questions on MLE, right? There will be 2 questions on MLE in the final exam in May or June of this year. So make sure it's important that's why I'm doing so many examples, because as you know, you learn things by practice, right? So that's why I'm doing these examples, right? Okay, the next example. So this is example number 12. Okay, guys, so this is, here you have a random sample from this PDF, and by the way, this PDF is known as the gamma distribution. You might have seen the gamma distribution in probability 1. If you haven't seen it, you can actually see more properties. You should go to the website. If you click on this link here, you will see there's something known as the gamma distribution, which is this one here, right? And the density function of the gamma is given by this formula here, right, which is precisely what I have written here. So this is exactly the same as the density or the PDF of a gamma distribution, right? There are two parameters for this. There's one k and theta, but I'm assuming that k is known, so the only parameter that is not known is theta, right? Okay, so the first step is, as usual, the first step is to write down the likelihood function. This guy here is the gamma function. I think I explained to you what a gamma function is. And there's also a video. There is a video about the gamma function. You should go back to the website. There's a video about the gamma function, which is this one here. So you can watch it when you have time, right? Okay, so this is the gamma function. Now, I'm not going to tell you how to simplify this, because please, once again, if you have problems, simplification of products of functions, please watch the video here. Please watch this video, this one, right? Okay? Now, if you simplify this, this is what you will get. All right? Yeah, I mean, some of you may wonder where this comes from, but this is what you should follow the rules. I mean, there are rules in mathematics, there are rules for everything. So if you follow the rules for simplification of products of functions, this is what you will get, right? Okay. All right. Now, when I take the log here, the log of the sum becomes the sum of the log, right? So that's why this guy here becomes this, right? Okay. Now, step number 3 is to take the derivative with respect to theta. And if you do that, you will get this is what you will get, right? Because remember, k is a constant, so all the terms that involve k only will disappear when you differentiate with respect to theta, right? So you set this to 0 and solve for theta, you get theta hat equal to equal to this, right? And this you can write as k divided by the sample mean, right? So that's step number 3, step number 3. Now step number 4 is to take the second order derivative, which is the derivative of this, right? So it's going to be minus nk divided by theta squared, which is a negative number, all right? So hence, okay. All right, guys? Yeah. Any questions on this, guys? Hello, talk to me, guys. Are you okay with this? Yeah, right. All right, next one. Example 12, example 13 now. This example is a little different from the previous examples. I will explain why. Suppose yeah, so here you have, you don't have this is not a random sample because you have xi having a Poisson distribution with parameter I times lambda for I from 1 to n. So you have n data points, but each has a different distribution. I mean, they all have the Poisson distribution, but the parameter is different. You see what I'm saying? So x1 will be Poisson with parameter lambda, x2 will be Poisson with parameter 2 lambda, x3 will be Poisson with parameter 3 lambda, and so on, right? Okay, so, but you can do this using this 4-step procedure, right? So I'll show you how. So the first step is to the product of the, in this case, because it's Poisson, it's a discrete variable, you're looking at the PMF, right? So you're gonna use this procedure here. So the probability mass function, I'm sure you did Poisson in the probability 1, right? So the probability mass function of this guy here is, I hope you do remember this. So this is the, what I have written here is the PMF of a Poisson variable with parameter I lambda. Yeah. Okay. Now, okay. Let me do this slowly because I know I have been doing things. Maybe let me do this simplification slowly. All right. This you have. I mean, I don't need to go so slowly, but just for the benefit of you, at least some of you, I'm doing this slowly just so that you can see what I'm getting up to, right? Okay. Right, so you have the product of three terms, right, divided by the product of xi factorial in the bottom, right? Now the product of this term here, let's look at this term here. What do you get if you take the product of this? Guys, talk to me. You get 1 plus 2 plus up to n times lambda. This is what you will get. Sorry. All right? Now, let's look at this guy here. What's the product of this? You can't actually simplify this, so you have to leave it like that. Some things you can simplify, something you can't. Yeah? It's the same. Now, let's look at this guy here. Can you simplify this using the rules? Come on, guys. This will be lambda. This is what you will get. Okay? And in the bottom, that is in the denominator, you have the product of this, right? And this you can't simplify, so you have to leave it like this. Right? Now, do you know something about this sequence here? 1 plus 2 plus up to n. What is it known as? Come on, guys, talk to me. Do you know, you should take the, let me show you. Do you know something called the arithmetic progression? Yeah? If you haven't, I mean, this is complicated, but the simple arithmetic progression is, it doesn't say it here, but anyway, let me write it down here. When you have 1 plus 2 plus up to n, right? This is equal to n times n plus 1 divided by 2. Had you seen this before or not? I mean, you can look this in Wikipedia or some other page, but I mean, this is a well-known fact, right? You've seen this, right, or not? Yeah. So this guy here, you can simplify to right? So this is the first step. Now the second step, are you guys okay with this so far? Yeah? All right, the second step is to take the log. Of this likelihood function. So that's what I'm going to do. I'm going to put it here. You can see this. So step number 2 is to take the log of L lambda. Now I'm going to do this quickly. I'm not going to waste my time. Well, I can do it slowly, but I hope you don't mind if I do this quickly. So if you take the log of this, right, this is what you will get. Right, this is what you will get. Okay, that's step number 2. Now step number 3 is to take the derivative with respect to lambda. Right? So it's to take the derivative of this guy here. So if you differentiate this with respect to lambda, you get minus n over n plus 1 divided by 2. And this is a constant. So the derivative of this is 0. And the derivative of this is simply x1 divided by lambda. And the derivative of this is also 0. All right? You follow me? So now, if you simplify this, or set this to 0, and solve for lambda, so I'm gonna call the solution lambda hat, right? So if you solve for lambda, this is what you will get. You will get 2 divided by n times n plus 1 times the sum of xi. Okay? Correct me if I'm wrong. You can also write this as 2 divided by n plus 1 times the sample mean. All right? Okay, so that's the lambda hat. Now, to make sure that this is a MLE, you need to take the second order derivative, which is the first order derivative of this. So it's going to be minus which is clearly a negative number. All right, so the conclusion is that hence okay, I know this example is a little different from the previous examples I did. Are you guys okay with this or not? Yes? Any questions? Feel free. Okay? So that's example 13. All right. The one example I gave you last Friday, remember during the review session on Friday last week, I gave you an example which I could not complete because of the time. Did you guys have time to complete it? Remember last Friday, I think I gave you, so let me do this if you haven't done it. This is the example I gave you last Friday. Suppose right? I think this was the example I gave you, if I remember. So let me show you the ln. ln is the log normal distribution. So if you go to this link here, and the log normal, where is it? Is here, this one. The log normal is this distribution here, right? The density, as you can see on the screen, right? So let me. I don't know whether you guys finished it or not, but in any case, let me do it. So the first thing you need to do is to write down the likelihood function, which is the product of the density of the log normal, which is this guy here on the screen, right? So with parameters theta and 1. Okay, so this is going to be 1 divided by xi square root of 2 pi, sigma is 1. Then you have e minus a half log of xi minus theta squared. Okay? You guys okay? So this is the formula I have used. Now, to simplify this, guys, you get this in the bottom, 2 pi to the power n divided by 2 in the bottom, and in the top you have half yeah. Okay, once again, I mean, I cannot repeat this enough times. Please, but I had many students having problems. I've taught this course quite a number of years. I've seen many students having problems with simplification of products of functions. So you may think it's easy, but when you come to doing it, you may make mistakes. So it's really important that you practice, okay? All right. You take the log of this function here, right? So it's going to be minus yeah. Okay. The next step is to take the derivative with respect to theta. This guy here is a constant. It has no theta in it, right? So it's 0. And this is also a constant, so plus 0. And this guy here, now, to differentiate this, I'm going to use the chain rule. I'm sure you know the chain rule, right? So you should use the chain rule for differentiating this. It's going to be 2 times log of xi minus theta times minus 1. This is what you will get. If you don't know what the chain rule is, please just look back in your calculus course. Right? Chain rule is common in calculus, right? So the 2 and the 2 will cancel, so this guy here will become, the minus and the minus will cancel, so this will become log of xi minus theta, right? Now take the sum inside, you get the sum of log of xi minus the sum of theta, all right? So this will be the sum of log of xi minus the sum of theta is n theta. Now you should set this to 0, right? And solve for theta, which I'm going to call theta hat. You're going to get 1 over n times right, this is what you're going to get. Now to make sure that this is a MLE, we take the second order derivative, which is the first order derivative of this. So this is going to be minus n, which is a negative number, right? Okay, so hence the conclusion is that all right, guys, are you okay with this or no? Come on, guys, talk to me. Are you okay with this or no? All right, so example 14. Now, maybe I have time for one more example. Example right. So in this example here, I mean, I have deliberately not given the. Remember, if you look at the procedure for MLE, it says that the likelihood function is the product of the density function. Now here we don't have a density function, so what do we do? So in order to find the density function, what do you need to do? You got the CDF, right, which is the cumulative distribution function. So how do you get the density function from the CDF? So you differentiate the CDF, right, with respect to x, right, and then you set x equal to xi, right? Now if you differentiate this with respect to x, you get what? You get a times 1 minus, I'm going to put xi to the power a minus 1. Okay? So sometimes the questions that you may get may involve the CDF, but you should not be fooled. I mean, sometimes it's easy to get fooled because people think that the CDF is the same as the PDF. No, it's not. The PDF is the derivative of the CDF, right? So you need to first find the density by differentiating it and then find the likelihood, right? Okay? So if you do the simplification, you get all right. So this is the likelihood. sorry, not COVID. This is the likelihood function, sorry, the log of the likelihood function. Then all right, set this to 0 and solve for A. You get A hat equal to minus yeah. Now the second order derivative is gonna be the second order derivative is the first order derivative of it, which is minus n over a squared, which is clearly negative, so hence sorry. All right, guys, so these are 15 examples. I think it should be enough for you guys. Maybe I'll give you a homework example. It's something you can try this at home when you have time. So this is example 16. I'm just running out of time. So example 16, suppose x1 to xn are IID, Ln with parameters theta, comma theta. Find the MLE of theta. Okay, guys, so try this at home when you have time. Okay? Okay, guys, any questions? Once again, please, if you haven't attended the lab sessions this week, there's a session at 2 p.m. today, so please do come to those because the attendance has been really poor in the lab sessions this week, right? So please do come to the session at 2 o'clock this afternoon, right? Right? Okay. All right, guys. See you later. See you next week or whenever. Any questions? Just come and see me. Okay. Yes.
I wanted to ask for the exam at the end. Will it be in-person exam or online?
Yeah, in person. Yeah.
In-person exam.
Yes.
Thank you.
Hi. What's up?
I'm stuck on next week's quiz.
Did you look at the last year's quiz?
Yeah, I looked at last year's. That one's, it seemed more simpler to me last year.
It's similar to the one I did today. It's similar to the one I did. Remember the one I did right now about a few minutes ago? This one here. An xi is Poisson with parameter I lambda, right? So try to follow this procedure and see if you can get it. I mean, I'm not supposed to help with the quizzes, but if you can try again and get back to me, I may be able to help you further.
Okay.
Yeah. Yes, what's up?
I was doing this question. It says with respect to the A, and it added all this. I'm not sure if I'm supposed to like take the A out or I'd take the
I
I.
squared, A squared, yeah, you can take it out.
But
But I squared, you can't take I squared out.
Right.
Yeah, there's a formula for sum of I squared. You need to look it up in Wikipedia.
That's fine.
You
Okay.
look it up in Wikipedia or
That's
something.
great. Thank you.
Yeah. Hello, sir.
So you know how we have like the log normal PDF?
Yeah.
Do we need to know that, or is that given
No.
as like a sheet, like in the exam?
In the
Would
exam,
we-
you'll be given that, man.
Okay.
So just, if you go to the course website, there's a link
Yeah.
which say there's only one page link.
Okay.
It says all the formulas you need to remember for the exam.
Oh, that is perfect.
Yeah. You know the course website, right?
Yeah, yeah.
Yeah, just I think it's near the second or the third link
Okay.
on the top, on the very top.
And it just says everything we
Right?
actually need to remember.
Exactly.
Oh,
It's
that's
only
so
less
perfect.
than a page.
Oh, that is so
Less than one page.
Thank you so
No,
much.
sorry. Yes, sir.
Just have one question, like, when we calculate, like,
Yeah.
kind of MLE, like the square or cube, that mean we should take these as a like,
You can
variable.
you can differentiate with respect to sigma. You look, sorry, you can lock me out, okay?
Yeah, I don't need it here. It's fine.
Yeah, you can differentiate with respect to sigma, sir. You don't need to differentiate with respect to sigma squared. You can differentiate. Thank you.
Yeah, see you.